Hello everyone. So today we'll continue our discussion on liquid-liquid extraction. So in the previous talk we discussed about the introduction, equilibrium, then equilateral triangle diagram for the single stage. Now in today's discussion we would be discussing on the multi-stage counter-current extraction process. Basically why we should go for multi-stage when will not meet the final requirement of the raffinate or extract phase, that if we can't achieve this much purity in one stage, so basically we should go for the multi-stage. That is the basic of this thing. So we can say that this particular process, multi-stage process, which is directly required with number of stages. Okay, now we have decided that we should go for the multi-stage, but how many number of stage would be required for the desired separation? Okay, so that is the fundamental of this multi-stage counter-current extraction process. So let's focus over here. uh, just see that this is stage number 1, stage number 2, and number of stage, which is capital N. You can see that first stage and final stage, and in between they have selected one of the stage which is n number of stage. And why they have kept this n number, so we'll discuss it later, that what is the importance of that. Okay, so we are having stage 1, 2 to n number of stages are there. Okay, so now basically we know that whenever we are doing any kind of designing, we must have material balance. Okay, so in previously we discussed about the single stage, that feed and solvent, that is been inlet, and raffinate and extract is outlet. So similar thing happening over here, that as you can see that on the left side this is feed and this is xf, which is the weight fraction of solute in the feed. Now it is counter current, so basically the solvent will come from the final stage. So here you can see that on the right hand side this S and YS, S which is the flow rate of solvent, YS which is weight fraction of solute in the solvent. And we know that after the operation we are getting raffinate as well as extract phase. So basically over here we'll get the raffinate, okay, and at the first stage we would be getting extract phase. Okay, see it is coming from this stage 1, that is why it is E1 and Y1, and this is it is coming from the final nth stage, so it is Rn and Xn. Okay, got it? So we have to imagine two envelope. Okay, let me clear this thing. So first we will imagine this total envelope 1. Okay, that is total material balance, and then after we'll imagine from this stage to n number of stage. Okay, so we'll meet some of the equation that would be helpful. Okay, so now let's first go for the overall material balance for the envelope 1, that I told you that this is overall. So that is F plus S, which is equal to Rn plus E1. F plus S equal to Rn plus E1, and by the mixture rule or lever arm rule, we know that when we'll add this feed and solvent, so we would be having some mixtures, okay, which is completely equal to Rn plus E1. Now we'll do the solute material balance. So it is Fxf Sys, which is equal to Rn Xn, that you can see over here in the figure, and E1 Y1, which is equal to m and the weight fraction of solute in the mixture, which is Xm. Okay, so from this equation we can come to know that what will be the amount of solute in the mixture, which is Xm equal to Fxf plus Sys divided by m. So basically m is nothing but F plus S. So from this first equation we'll come to know that what will be the amount of solute in the mixture. Okay, that is the similar procedure that we have to follow, that we followed in single stage. Okay, now next thing we'll focus on this again. I'll tell you that is envelope 1. You can see over here 1 to n. Okay, that is total stages. Okay, so here I can also write down that, see, overall material balance, it was, we know that F plus S equal to Rn plus E1. Okay, but from that equation I can also write down that F minus E1, which is equal to Rn minus s, okay, which is completely mathematical. And what will imagine that this difference, now see in this figure, so difference in this feed flow rate and extract flow rate at stage 1 or before the stage 1, and over here you can see that difference between this Rn and S, that is the difference at the final. So that is the imaginary difference that with the help of this extract flow rate and this feed flow rate we are having this difference, that is nothing but will indicate with this D point. Okay, so just imagine that this is the difference F minus E1, which is equal to Rn minus S, which is equal to D, that is the difference. And here we can say that this difference that we are getting in the flow rate, which is similar at this stage, and we can say from another equation. Now see that envelope number 2. So what is envelope number 2? That is up to this small n stages. Okay, again we'll write down that material balance. So I'll just write down F plus, now that see here what is the entrance over here, which is the extract from the previous phase, right? So F plus E n plus 1, which is equal to Rn plus E1. So that is the total material balance from stage 1 to small n. Here again you can see that F plus En plus 1, which is equal to Rn plus E1. Okay, so again based on that what we did in previous equation, we can follow the similar method over here, that F minus E1, which is equal to Rn minus En plus 1, which is again I just told you that let's assume this difference is D. So based on all this equation we can imagine that the difference at all the stage or after all the stage that we are getting, which is similar, which is F minus E1 equal to R1 minus E2 equal to R2 minus E3 equal to Rn minus En plus 1 equal to Rn minus S. Okay, so we can say that the difference after all these stages we are getting in feed and extract or raffinate and extract, that is similar, so that we can indicate with this D point. Okay, so right now you have to remember this thing, that the difference is similar. And here we can also say that first, that is F minus E1, that is okay, but if we'll follow this stage wise, so we can see that R1 minus E2, R2 minus E3, which is indicated with this n stage Rn minus En plus 1, En plus 1, that you can see over here. Okay, so that is the one more parameter that we have introduced in this derivation. This is the difference point. Okay, so difference at all the stages in between the flow rates are similar, as you can see over here. Okay, so now what's the use of this difference in the equilateral triangle? Okay, so we'll check that. So now basically we will follow the method that how should we start in this equilateral triangle. Okay, so this is one triangle. Okay, now this is binodal curve which we got from this LLE data and solubility data that we have been given, or we know that we can find it from any of the sources. Now what is the first step that we did yesterday, or that we did in this single stage extraction? That is, we have to join this S and this F point. Why? Because these are the inlet, F and S are the inlet. Okay, so basically we will join this point based on the composition. So which are the composition? XF and YS. Okay, as I have written over here, S YS F XF. Okay, and we can find this XM. How? See that by joining this point, now we know that this is the equation, XM equal to FXF plus SYS divided by F plus S. So all these parameter are known to us. Okay, so we can come to know that what is XM point. So this XM, that we can locate M point on this line only. Why? Because f plus s which is equal to m. So all these points should be on the single line. So that is the repeated process that we did in single stage. Okay, so this is on fs line and that I have indicated. Now listen, now we know that this is the overall equation, yeah, right? F plus s equal to Rn plus E1 which is equal to mixture. Okay, so always, it's not always, generally out of this 4 parameter we know the 3 of the parameter, okay, and then we can find the 4th parameter. But how we should find that, that is very important. So here I have written that generally 3 parameters will be known. So let's assume that the f which is the feed, okay, that already we know that this is s and this is Rn. So what is this Rn? Just see here. So if some designer, if he or she will tell us that I want in the feed if it is 50% and I want at the final it is 4%. Okay, so this is my feed composition and this is my raffinate composition, that from 50% to 4% I want require the removal of this thing, right? So basically we know that we are having this xf data and we are having this xn data, that is 4% which is in the raffinate. Okay, so we can say that we are having this f s. Yes, again s is again important, it can be unknown for most of the time. So s which is the flow rate of solvent, but here we are assuming that s is known to us. Okay, so this is our first type, that we are having this f, s and Rn data. Again I am repeating how we can get this Rn data based on this particular weight fraction. Okay, so what is that weight fraction? That I want this separation, so from the feed 50% to 4%. Okay, so at the outlet I want 4%. Okay, so rest of the solute would be extracted. Okay, so this is our raffinate phase, so it is Rn. Okay, so now let's move forward. So this is known to us f, s and Rn. Okay, so let me change the page. So as I just told you that we know f, s, Rn. So this first procedure by joining this f and s line, that is done to us, and indication of m, that is again done. But now new point which is Rn, that is nothing but the composition or weight fraction of solute. Okay, so now I'll indicate Rn somewhere over here, which is in a very less amount. As you can see that it is just 4%, so it is 0.04, that is why it is somewhere over here. And again we know that what is the material balance, Rn plus E1 which is equal to m. So definitely this m point, again it should be on this Rn and E1 line, but this m point which is already available with us from the fs line. Okay, so what we should do now, this m point is known to us, this Rn point is known to us, so simply we'll join this Rn m point and will extend this line up to this solubility curve. So this point that we will get, which is our nothing but our extract point. Okay, so here we can say that it is our y1, right? So this is how we can indicate that what is E1. Okay, so now this is only for the one of the final stage that we have come up with. So how many total number of stage that would be required, that is very important. Okay, what we read here, that is the overall, that in between this thing we are having the overall number of stages, right? So how to find out overall number of stages, which is again very important. Now again I'll repeat, now we are having this f, E1, Rn as data available with me. Now if you remind that thing, that if we are having this one data and if we are having this distribution curve which is nothing but y versus x, that is amount in extract versus amount in raffinate, again which is available in LLE data. So if we'll plot this curve and if we are having this one of the point E1, okay, so I'll expand this up to this curve, if I'll go downwards and if I'll come over here, so this will be my R1 point, right? Because E1 and R1 are in equilibrium. En and Rn are in equilibrium, that is based on the solubility curve. Okay, so now what I'll require that from this E1 I am getting this R1 point. So that is our next step. From all this procedure, now we have come up with this new point which is R1, which is equilibrium with this E1, and that we got from this distribution curve, as you can see over here. Okay, so this is our, here we don't require any trial and error method because we know one of the point which is E1. So from this E1 we can come to know that what is our R1. Okay, so now what is the importance of this R1? As you can see over here, we discussed earlier that F minus E1, which is equal to Rn minus En minus 1, which is equal to Rn minus S. Okay, so now if I'll write down, let's take n equal to 1. So if we'll apply that n1 over here, so it will be R1 minus E2, which is equal to D. Okay, which is equal to D. So the common thing is D. So why can't we go for this D point? So then we can come to know that what is this En plus 1 point. Okay, so now let's focus on this D point, which is again important. So I'll write down this equation again, F minus E1, which is equal to Rn minus S, which is equal to Rn minus En plus 1, which is equal to D. So now focus on this first step, F minus E1 equal to D. Okay, so I'll compare this thing with F plus S equal to M. So here we knew that on Fs line M was the middle point. Okay, so now we are having this equation F minus E1, which is equal to D. So here what is the middle point? As you can see that F equal to D plus E1. So this F will be the middle point. So now among these three parameter we are having F and E1. Okay, so as you can see that this is F and this is E1. So if I'll join this F and E1, so at the extension I would having some point, but at which point? Okay, so similar, this is Rn minus S. Rn minus S equal to D. Okay, so I can write down Rn equal to D plus S. Again both are known to us. Okay, so I'll join these points Rn and S, Rn and S up to some extent. So the point at which this both the line will intersect, which is called the difference point. Okay, we are indicating it with D. In some of the book it is delta, in some of the book it is delta Rn. Okay, which is nothing but the difference point. So that was the step, that how to come up with this D point. Okay, so this D point, which is nothing but this F, E1 and RNS line intersects. Now we will use this D point. Okay, I'll write down. Now let's go for the next step. See here, I'll write down this D. Now we have focused on this particular two equations only. Now go for this third equation. Okay, so this is, here I have written this third equation, and I have written that n equal to 1. Okay, so here it will be R1 minus E1, which is equal to, it's not 0, it's D. Okay, so again from this equation we can write down that R1, which is equal to D plus E2. Okay, so R1 will be the middle point. So in this thing we are having R1 as well as D. So R1, from where we got this R1, that is from this, you can see that distribution curve. Okay, so we are having this R1 and we are having this D. So I'll join this D point as well as this R point, and I'll expand this or extend this line up to this solubility curve. So it is nothing but R1 is equilibrium with R1, which is on the line of this D, as like this equation R1 minus E2, which is D. So this point that we will get, which is our E2 point. Okay, so now by joining this D R1 we are getting this E2 point. So the next step, that how to come up with the R2 point. So again we'll follow the same procedure. From that distribution diagram I'll expand this thing, okay, then I'll come over here and somewhere around here I'll get this R2 point, okay, that are equilibrium. This E2 and R2 are equilibrium. So now again from R2 to D point I'll join that thing, and here I'll come up with this E3 point, okay, by using the similar equation. If I use n equal to 2, so R2 which is equal to D plus E3, so I'll get this E3 point. And likewise we need to continue this procedure up to this Rn point. So what is this Rn point? That is our final refinite. So when we will achieve this final line, up to that point we should follow this method, okay. So you can see over here, it is from one of the book, that at the end we are getting this kind of curve. So here you can see that this is the final line that we are getting, okay. So here you can see that the number of line starting from here, from R1, 1, 2, 3 and 4. So we are having 4 number of stage that would be required for the desired separation. That is the fundamental of this multi-component counter-current extraction, okay. So this will be your final graph. This is how you have to follow the procedure. And the last discussion of today's lecture, that we just discussed the theory that this will be the known parameter all the time, that what will be the feed flow rate, composition in the feed and composition in the solvent. But these are the parameters that we should determine, okay. How we will determine that? Two of the parameters that will be known to us and two of the parameters that we will find. So far what we discussed, that this just see here, that was n value was known and xn or y1 value was known. So we were having this xn value that was known to us, that is Rn, and based on that what we find, which is n, okay, number of stage that would be required. But we can have this different option, that we are having known value of xn and y1, that Rn and E1, this value which is given to us, and from that again we can find out this n plus s method just by changing some of the root, nothing else. If we'll follow this third method, in that method we have given this solvent as well as this n, okay. So remember that the method in which we have to find this both the data xn as well as y1, or we can write down Rn and E1. So in that method we have to go for the trial and error method that we followed in the single stage, okay, and this is the final method. So this can be the combination, but here we have just discussed that if we have been given this s, if we have been given xn or y1, so we can find out this number of stages for the multi-component counter-current extraction, okay. So that was the procedure, and based on that we can solve the example. So thank you so much.